All right, guys, welcome back for part 2. So if you missed part 2 of the exam, here's part 2 of the exam. Part 2 is on kinematics in one dimension. So it says the one way that mathematical models are used by scientists and engineers is to make predictions about how a system will behave. In the video, the engineers used a simple kinematics model to predict how much the glider would need to accelerate as it is pulled along the runway in order to launch. Based on the aerodynamics of the glider, the engineers calculated it would need to reach a speed of 40 miles per hour to successfully launch into the air. 40 miles per hour converts to 17.88 meters per second to successfully launch into the air. The roof is 160 feet above the ground, and the runway was about 60 feet long. 60 feet long converts into 18.3 meters. The first question the engineers need to figure out is if it is theoretically possible to reach the desired speed given the length of the runway and the height of the tower. Given this information, so question number 1 says, given this information, what must the acceleration of the glider be to reach the launch velocity by the end of the runway? Convert all values to SI units. So I converted the first two to SI units for you. I need to convert 160 feet to SI units for you. Give me just 1 second. 160 feet times 0.3048 is 48.7 meters. So everything has been converted to SI units for you. So for the first one, we know that the velocity we want to reach by the end of the runway is our final velocity. And it says that velocity is 17.88 meters per second. We start out from stopped. We start out from just sitting at the front of the runway. So our initial velocity is 0 meters per second. We're looking for acceleration because it says, what must the acceleration be? So I'm going to put a big question mark by acceleration. And it says by the end of the runway. So how long is the runway? The runway is going to be built from tables on the peak of the roof, and it's 18.3 meters long. So my displacement is 18.3 meters long. So now we have 3 out of 4 kinematic variables. So you can pick a kinematic equation and you can solve for acceleration. It says the engineer wants the glider to accelerate at a rate of 1.2 Gs. So that means he wants the glider to free fall at a rate of 1.2 Gs, which is 11.6 meters per second squared. How does this compare to your result? Ignore what I said about free fall. The engineer wants the glider to accelerate at a rate of 1.2 Gs. How does this compare to your result? So is this number bigger than your number, or is this number smaller than your number? So you're either going to say this number is bigger than my number, or this number is smaller than my number. And why would the engineer overestimate the acceleration? There's something that we aren't accounting for in physics, and we aren't accounting for when we're working this problem that exists in the real world when you're outside on the top of a building. So we're going to account for that in the real world, but we're not accounting for that in this problem, and that's why we're going to overestimate. So write that down as your second part to this answer. Let's go to the next page. Here's what I was explaining on the next page before. Is it possible for the bathtub to accelerate at 1.2 Gs? So he wants the bathtub to accelerate at 1.2 Gs. So he wants the bathtub to fall at 1.2 Gs, or at 11 what did we say it was? 11.6 meters per second squared. Gravity pulls everything down at 9.8 meters per second squared. So can something free fall faster than gravity? So explain why or why not. Can something fall faster than gravity? Why or why not? Ignore the second part to this question. Do not answer the second part. Number 4. Why would you use a scale model to test your ideas? So why would you use a scaled down model to test your ideas first? So in the scale model, before they built the big model of this glider, they built a small glider that was about 3 or 4 feet long, and they used a bathtub filled with water instead of a bathtub filled with concrete. And they tested it with that model first. Why do you think they used a scaled down model to test their ideas first? So that's the first thing you're going to write. So you're going to write down first why you think we should use, or why would you use a scale model to test your ideas instead of going with a full out model first. Then I want you to give me 2 benefits to using a scale down model, and I want you to give me 2 cons to using a scale down model. So you're going to write why you would use a scale down model. Then you're going to give me 2 benefits to using a scale down model and 2 cons to using a scale down model. All right, question number 5. The engineer's solution to the problem of not being able to accelerate faster than gravity was using a double pulley system. Using this system, the distance traveled by the bathtub is half the distance traveled by the glider. What does this tell us about the acceleration of the glider relative to the tub? All right, so we know that gravity can only pull something, something can only fall as fast as gravity. So that means this can only fall down at 1 G, which means this can only accelerate at 1 G, or 9.8 meters per second squared. But the ingenious engineers decided to use a double pulley system, and they wanted this to accelerate at 1.2 Gs, or 11.6 meters per second squared. This is double the length of this. So each of this is 1/2, and this is 1/2, and this is the whole. 1 plus 1 makes 2, or 1/2 plus 1/2 makes 1. So if we divide this by half, this accelerates at 0.6, and this accelerates at 0.6. So the whole thing accelerates the glider at 1.2 grams. The acceleration of the glider relative to the tub can be proven with the kinematic equation: change of displacement equals velocity initial time plus 1/2 acceleration time squared. Velocity initial time cancels out, so you get your displacement is equal to 1/2 acceleration time squared. So your displacement is equal to half your acceleration. My displacement is equal to half my acceleration. There's nothing more to solve on this problem. That is the answer. Number 6. What is the height that the bathtub must fall in order for the glider to reach the desired launch velocity? How does this compare to the height of the castle roof? Will the glider reach 40 miles per hour before the launch? So let's dissect this and do this one little bit at a time. So let's start with what is the height that the bathtub must fall in order for the glider to reach the desired launch velocity? So what is the desired launch velocity? The desired launch velocity was written a couple pages before. We also had it on our first kinematic problem. The desired launch velocity is this 17.88 meters per second. So we're going to write down 17.88 meters per second. The plane still starts at 0 meters per second. It says, what is the height? So we're looking for displacement. Oh, that should be a question mark. And we know what the acceleration is. We said up here, we wanted our acceleration to be 11.6 meters per second. So I want my acceleration to be 11.6 meters per second squared. So I want to find a kinematic equation and I want to solve for displacement. And it says, how does this compare to the height of the castle roof? So if we go back to our introduction, we know the height of the castle roof was 48.7 meters. So our castle roof was 48.7 meters above ground. So will my glider reach 40 miles per hour before launch? So if my glider needs more than 48.7 meters of displacement, so if my displacement is greater than 48.7 meters, it will not reach 40 miles per hour. But if my displacement is less than 48.7 meters, it has plenty enough room to fall the right distance. So if my displacement is less than 48.7 meters, it will reach the 40 miles per hour it needs to reach, and we will successfully launch. That is all of part 2, and that is all of kinematics for your midterm.